This is Professor Keene. We have been looking at Chapter 7 in A Student's Guide Through the Grade Physics Texts, Volume 3. In this chapter, Hans Christian Oersted is describing the effect that a current-carrying wire has on a magnetic compass needle. We are on page 78 in the text, and in the first full paragraph, he describes his fourth experiment. That is, he places a compass needle beneath a current-carrying wire and tries to place things between the compass needle and the current-carrying wire to see if the effect can be blocked. And there he says, the effect of the uniting wire passes to the needle through glass, metal, wood, water, resin, stoneware, and stones, for it is not taken away by interposing plates of glass, metal, or wood. He says that even glass, metal, and wood interposed at once do not destroy and indeed scarcely diminish the effect. And he goes on to mention a few other materials. He also takes the compass needle and places it, he says, in a brass box that is filled with water, and yet still the compass needle turns when the current is turned on in the wire. So it seems like the brass-filled box with water has no effect. Whatever is causing the turning of the compass needle is not blocked by any of the materials that he tests. This, by the way, is more evidence that the effect he's observing is something completely new, because after all, electrical effects that we're accustomed to with charges are easily blocked by other materials. Next, he goes on to his fifth experiment, and here I'll make a sketch, and I won't draw the entire apparatus like I have been doing. Allow me to just draw the uniting wire, like this. This is his, by the way, his fifth experiment. This isn't how he numbers them, but I think it's convenient for us to number them. In his fifth experiment, he again hooks up one side of this current-carrying wire to the positive terminal of the battery, the other to the negative terminal of the battery. But now what does he do? Instead of having the compass needle placed beneath it, he hangs the compass needle above it. So this would be the direction that the compass needle points. Let me put some compass directions here to remind you. That way is north, east, west, and south. And again, this wire is placed in a horizontal plane, and let me draw a plane like this, by the way, that represents the plane of the local meridian. So you can imagine if we draw a vertical plane that lies along the north-south axis, this is called the plane of the meridian. I'm writing this down because he describes declination of the needle as deviating from the plane of the meridian. So he notices that when you put the wire below this magnetic compass needle and you turn on the electrical current, let me draw an arrow representing the direction of the electrical current through the wire, so that's the current. What happens to the compass needle? Well, in this case, he notices that the tip of the needle swings toward the east. Remember when you placed the compass needle below the wire, the compass needle was found to swing to the west. So it swings in the opposite direction when placed above and below. So let's go on to his sixth experiment. In his sixth experiment, you might anticipate what he's going to do. He says, what if now, instead of placing the compass needle above or below the current-carrying wire, what if we were to place it in the same horizontal plane as the wire? So I'm going to draw a plane like this. This would be the horizontal plane. Like this. And if you place this compass needle, if you kind of suspend it right next to this current-carrying wire, like this. So again, this is the positive and negative ends. And so if we draw an electrical current in this direction once again, what happens to the compass needle? Well, in this case, he finds that the compass needle experiences a downward dip. So let me draw these other compass directions just to be as clear as possible, because it might not be obvious which way my arrows are pointing. This would be the up direction, vertically up, and this would be the down direction. And he notes that when the compass needle is suspended to the east of the uniting conductor or the uniting wire, what happens is that the compass needle, the compass tip, rotates downward. So there's a dip. I think he calls it an inclination of the, or a declinate, yeah, an inclination of the back. Okay, calls that I think he calls that an inclination. Okay. And what about if, on the other hand, you were to place this compass needle to the west? Okay, so I'll draw, I guess this would be his 6th and 7th experiments. When you place it to the west, what happens? Well, the tip, as you might imagine, goes upward. So when to the west, the tip points upward. I think he phrases it a bit differently. I think he talks about if the wire is to the east or west of the compass needle, what it does. I'm writing it as if the compass needle is to the east or west of the wire, which way does it point upward? Okay. All right. And then finally, there's another experiment. So this would be the 6th experiment and the 7th experiment. We might call those 6th and 7th. And what about, where does he go from here? What is his 8th experiment? We're going to skip a few experiments. So we'll say, let's skip a few. He has a number of different experiments on the bottom of page 78, on the top of page 79. I don't want to go through all of those, 78 and 79. And let's call the next one this 8th experiment. What does he do? Well, he does the exact same kinds of experiments, but instead of using a magnetic compass needle, he uses needles that are made of brass and glass and gum lac, probably some kind of shellac, maybe a hard resin of some sort. In other words, he uses non-magnetized needles. So non-magnetized needles. And he notices that those do not experience any of the effects that he has been talking about. So they do not experience an effect when the electrical current is turned on. So this has clearly something to do with the fact that we're dealing with a magnetic compass needle interacting with this electrical current flowing through the wire. So what happens then? Well, what Oersted does is on page 79, he tries to offer an explanation of this in terms of what he calls, once again, this electric conflict. He says that there's some electric conflict that is not confined to the wire, but it is dispersed widely around the wire. There's sort of an environment, an invisible environment that's created around the wire that has an effect on this magnetic compass needle. He says it is sufficiently evident from the preceding facts the electric conflict is not confined to the conductor, but dispersed pretty widely in the circumjacent space. And he goes on to say that it seems like this electric conflict forms circles about the wire. So this is Oersted's picture, a mental picture you might call it, of what is happening. He says if you have this current carrying wire like this, what's happening if there's a positive terminal attached to this side, a negative terminal attached to that side, you have this electrical conflict that's in a sense swirling around the wire in circles like this. And this circle represents something going around the wire that acts on the compass needle so as to deflect it in this particular direction. So if you were to put the compass needle up above it, it would deflect to the right. If you were to put the compass needle to the, let me draw some axes here, like this. So if you put the compass needle over here, it would deflect downward. If you were to put the compass needle over here, it would deflect leftward. If you were to put the compass needle over here, it would deflect upward. And once again, if you put it above, it deflects to the right. So there's some directionality that is implied by this electric conflict, he says, swirling around the wire. Now remember that the compass needle doesn't exactly point sideways over here because it was originally pointing in the north-south direction due to the magnetism of the Earth itself. But this represents the tendency that is created by this current carrying wire to make it deflect away from its original orientation toward sideways or down or the other way or up. So he even describes this because, this compass needle is at sort of a 45-degree angle, he mentions. He imagines these spiral lines going around this current carrying wire. So I'll draw another picture that represents not merely the tendency of it to turn sideways, but the actual direction that this compass needle is going to be facing due to a combination of the effect of the electric conflict around the wire and the direction that it would ordinarily face due to the magnetic behavior of the Earth itself. Okay? So those are the experiments that Oersted carried out, and he describes in this paper from 1820. In the next lecture, what we're going to do is start talking about the work of Ampere. And Ampere is going to pick up where Oersted left off here and provide a better understanding of the magnetic behavior and the forces exerted on magnets by electrical currents.